Today we'll be talking about momentum and impulse, which is the change in momentum. Momentum can be defined as the product of an object's mass and velocity. Sir Isaac Newton discovered momentum before he wrote his three laws of motion. In fact, momentum became part of one of his laws. Inertia is an object at rest tends to stay at rest, so the flip side of that, momentum is an object in motion tends to stay in motion. This is why we can think of momentum as moving inertia. Inertia keeps an object in place. Momentum keeps an object moving until there's an outside unbalanced force. The more mass an object has, the more inertia it has, so the more momentum. If it's hard to move something heavy, that means it's going to be hard to stop it when it's already moving. Likewise, the faster an object moves, the more momentum it has. Since it's just the product of two variables, mass and velocity, if you increase one, the momentum's going to go up. If you increase both, the momentum's going to go up a lot. Brainstorm an answer to the question, which has more momentum, a slow-rolling boulder or a fast-moving bullet? Keep in mind things like mass versus velocity. One has more mass, one has more velocity. We'll do a think, pair, share with this in class tomorrow. The momentum formula, as we said, the definition of momentum is the product of mass and velocity. The formula is just that. Momentum, which is represented by P, is mass times velocity. Momentum can either be positive or negative, depending on which direction it's going. Velocity can be either positive, it's forward, or negative, it's backwards, or up or down. Since an object usually does not keep a constant velocity, when we calculate the momentum, it's at a specific point in time. In many cases, it's right as it collides with another object, so we can look at the conservation or transfer of momentum. Conservation of momentum is a rule that states the total momentum before a collision is equal to the total momentum after a collision. This is within the object itself and whatever object it collides with. So let's look at an example. Newton's cradle is a very common example of the conservation of momentum. Before and after, we need to consider both. So let's look at the first ball and the last ball. The first ball has a positive velocity. It's going forward. It has the same mass. All the balls in this case have the same exact mass. The mass is not going to change anything. So we can find the momentum by taking its velocity and its mass and multiplying. The last ball right now, before, is stopped. It has the same mass, so mass is not an issue. It has no momentum because it's not moving. You either have to have mass or velocity. Actually, you have to have mass and velocity in order to have momentum. And these are just qualitative observations. If we wanted to, we could attach a number to the velocity of the first ball. The second ball, or the last ball I should say, is at 0 meters per second. It's stopped. The first ball at the end stops. When it collides, it stopped. It still has mass, but now it has no momentum. Where did all that momentum go? It traveled through the balls in the middle all the way to the ball at the end. Now the ball at the end is going forward, so same positive velocity. However fast the ball went in, that's how fast it's going to come out. So it has the same momentum as the ball at the very beginning. The impulse of an object is related to the momentum. If we change an object's momentum, we call that an impulse. It's the change, or delta. So it's the change in momentum. We subtract the momentums to find the difference. Change in the momentum involves either changing the mass or changing the velocity. More often than not, you'll see a change in velocity. When an object collides with another object, it's either going to stop, change directions, or slow down. Impulse is the reason that you bend your knees when you jump down from something. Your impulse is the same, but by increasing the time, you decrease the force. Impulse is directly related to time and force. This is also why you follow through when hitting a baseball or kicking a soccer ball. The force is the same, but by increasing the time, you can increase the impulse. So it goes from a low momentum to a higher momentum by increasing the amount of time that you're connecting with the ball. There are a couple different times you'll use impulse equations. When you have the change in the momentum. So you have an initial momentum and a final momentum. A momentum before a collision, momentum after a collision. You subtract those to find the change, the difference in momentum. That's going to be equal to the force times the time. So impulse equals force times time. This formula helps you either solve for impulse if you have the force and the time that it was in contact with another object, or if you know the impulse already and you need to find the amount of time it was in contact or the force that's being applied. Another formula that we use with impulse, the change in p, so again the change in momentum equals mass times the change in velocity. This is just an adaptation of the momentum formula. Momentum is mass times velocity, so if I want to find the change in momentum, which is the change in mass, or sorry, change in momentum, I'm going to multiply mass times final velocity minus initial velocity, the change, the difference in velocity. Remember, mass is not going to change very often. Another formula is just the basic. If I know the final momentum and I know the initial momentum, I'm going to take final minus initial. Final can sometimes come after an object slows down or sometimes after an object has collided with another. Just like the kinematic equations, we decide which formula to use based on what we're solving for and based on the given information. Let's try an example problem. A tennis player returns a 30 meters per second serve straight back at 25 meters per second. So it changed from 30 meters per second to 25 meters per second. It slowed down after making contact with the ball for 0.5 seconds. So they followed through. If the ball has a mass of 0.20 kilograms, what's the force she exerted on the ball? So a hint, what's the change in velocity? So we're going to look at our formulas that we have. Impulse equals force times time. Well, I have time, but I don't have force. Impulse equals mass times change in velocity. So v minus v sub 0. Well, I have a final velocity, I have an initial velocity, and I have a mass. The last formula, p minus p sub 0. So final momentum minus initial momentum won't work in this case. Once you decide on your formula, simply plug and chug. Write out the formula and replace each of the variables with the appropriate value. The mass of the object, or the tennis ball in this case, is 0.2 kilograms. The final velocity is 25 meters per second. The initial is 30. Now, since it is return, it's going backwards. Forwards would be positive, backwards is negative. In this case, all of our problems all of our values are on one side of the equation, so it's just an order of operations. We're going to do 25 minus negative 30 to get 55. Multiply that by 0.2 to get an impulse of 11. Our momentum changed 11. So we need to find the amount of force exerted. I have the impulse. I'm looking for the force. I'm given the time. So I can plug all that in. Impulse is 11. Force is unknown, so it just remains a variable. Time is 0.5 seconds. It was in contact, the racket and the ball, for 0.5 seconds. In this case, my variable is on one side and I have values on both, so I do need to solve. Ask yourself what's happening in my variable. I'm multiplying f times 0.5. To undo that, I'm going to divide by 0.5 on both sides. So it ends up applying 22 newtons of force. This 22 newtons is what causes the momentum to change. It's what causes the ball to increase or decrease after it hits the wall.